Hi, and welcome to today's video. Today we'll be looking at weather hazards and climate change. In this lesson, we'll be covering a lot of different topics. Starting with climate change, we'll be looking at the natural and human causes, as well as the impacts on people and the environment, and the various greenhouse gases and their impact. Then we're going to be looking at atmospheric circulation cells. Following that, we'll be looking at cyclones and investigating the social, economic, and environmental impacts of cyclones. And then finally, we'll be looking at droughts, seeing what the human and natural causes are, as well as what the impacts of droughts are on people and the environment. To start, let's look at climate change. When discussing climate change, you'll typically delve into the discussion of greenhouse gases. So the question now is, what is greenhouse gases? So a greenhouse gas is a gas that contributes to the greenhouse effect by absorbing infrared radiation. If you think of a greenhouse, the glass keeps the inside warmer by absorbing some of that infrared radiation. So similarly, there are gases which do the same for the whole Earth. In the bottom, we can see the primary greenhouse gases in Earth's atmosphere. Things like water vapor, carbon dioxide, methane, nitrous oxide, and ozone. These are the greenhouse gases. So anytime we talk about climate change and the topic of greenhouse gases arise, we can now understand it as gases that absorb infrared radiation, similar to that of a greenhouse. Now let's look at the human and natural causes of climate change. To understand how humans can have an impact on climate change, we first have to understand how exactly humans produce energy. There's many different ways, but we're going to be focusing on thermal energy. Thermal energy requires three main chambers. The first chamber will contain water, and using oil, nuclear, coal, or gas, that water is boiled, creating steam, which then, through pipelines, is led into a second chamber that has these turbines. So as that water begins to boil and collects the steam up, you'll find that it's pushed into the next chamber, which causes those turbines to spin. As the turbines spin, they will spin the axle. And that's important because in the third chamber, there is the same mechanism you would find in a dynamo. There's copper wire and there's magnets. When they revolve around each other, you've got yourself electricity. So as those turbines begin to spin, they will spin the axle and in turn cause the magnets to move around the copper wire, and that produces electricity. It is recycled and you get this nice little system. As we heat up the water, it produces the steam then moves the turbines moves the generator, and then from there you've got yourself electricity. We can see this in effect in a nuclear power plant. Here we can see in the first chamber on the left how uranium fuel is used to boil water through steam generators, and that steam being transported through steam lines will move turbines in the second chamber. Those turbines connected to an axle will move magnets and copper wire around in the generator, which will produce a charge. That charge, once it has gone through a transformer, will eventually become electricity that we use in our houses and our businesses. What we want to focus on is this: the water vapor which is produced as this process goes out. So here we can see exactly how energy production releases greenhouse gases in the atmosphere. So as our demand increases, people will need to meet that demand by producing more things, which will result in more energy, and that is how water vapor, or the greenhouse gas, is introduced more into the atmosphere. Switching to physical causes, we can see, for example, how a volcano can exhibit lots and lots of greenhouse gases into the atmosphere. And what happens is, as that volcano begins to erupt, all of those fumes, all of those ashes, they are actually packed with lots of greenhouse gases, namely ash, water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide. All of these are being emitted into the atmosphere, and those are a huge contributor of greenhouse gases. So a natural cause can be a volcano. Now let's focus on the greenhouse effect. To understand this, we're going to be looking at the greenhouse effect, followed by the enhanced greenhouse effect, starting with the greenhouse effect. Now, the Earth will receive energy from the Sun in the form of short-wave radiation. From here, the Earth will absorb some, but if it takes too much, we'll burn and we'll all die. So instead, what will happen is we will take some, but we will re-radiate some of that back into space in the form of long-wave radiation. So here we have a nice healthy balance. We take what we need, and the excess is sent back into space. That is the greenhouse effect. It gives us a balanced temperature, balanced climates. It's quite good and we like it and we really depend on it. The problem is, now that we're going to switch to the enhanced greenhouse effect, we can see how things like population increase having higher and higher demands. As the people increase, they need more houses, more TVs. Now I need the latest smartphone. Now I need the new car. Now I need a second car. I'm bored. I want to buy the new gaming console. I need a washing machine and another microwave. There's a new fridge. All of these demands will produce more and more demand on energy. And as that energy demand starts to be met, we'll find that more and more of the water vapor will be exhibited in the atmosphere, and that will start to pack on and thicken that layer of gases around the Earth. And you'll see that as we begin to thicken all of that atmosphere and that greenhouse gases, less and less radiation is able to be re-radiated back into Earth. Now, if it's not being escaped from the planet, it's staying here with us. And that is essentially the enhanced greenhouse effect. As we introduce more and more greenhouse gases, we'll find that it's harder and harder for the energy we get from the sun to leave the atmosphere and go back into space. So instead, it stays and lingers with us, causing us some problems. In this graph, we can see how around the 1900s, that is when the temperature began to really spike. That's also around the time where we started to really mass produce things. We used to have mass production of cars, aeroplanes. That's around World War I, one of the first really industrialized wars, where people dedicated all of their ingenuity, all of their engineering and science to mass produce guns, ammunition, bombs, planes, trains, telecommunications, things for transport, ships. All of that was produced around that time. And that's when the trend started really beginning. And then from there, we can see how it just continued to grow and grow and grow. And all of that is producing excess greenhouse gases, which the Earth is causing to it lingers in the atmosphere, and it prevents less and less radiation from leaving. Now let's look at the causes of climate change, starting with transportation. As the number of cars begin to grow on the road, every time that car will use fuel, burn it for energy, the byproduct seen through the exhaust pipe is actually a greenhouse gas. So things like aeroplanes, buses, trucks, and cars all produce greenhouse gases through the exhaust through the process of burning fuel. So some cities like Birmingham and Bristol have decided to incentivize not taking a personal car. So they'll say things like, we'll make it easier and cheaper to take your bike, to rideshare, to take the bus. And all of this is in a bid to reduce the greenhouse gases that come from transportation. The next one is fertilizers. With fertilizers, we're looking at the production of fertilizers in this particular point. As you produce fertilizer, there is a byproduct, namely carbon dioxide and nitrous oxide. The next one is natural gas drilling. To extract natural gas, it also releases methane, which is a greenhouse gas. So the more they start to drill for natural gas, the more methane is released. The next one is permafrost. Now, permafrost is when the ground is completely frozen for about 2 years. If the temperature increases, it will melt and all of the carbon trapped inside will begin to release. So permafrost is actually a contributor of climate change. The next one is deforestation. We understand trees as being carbon soakers. So if we keep deforesting, there'll be less carbon soakers, so there'll be more carbon in the atmosphere. The next one is volcanic eruption. We saw this one a bit earlier. As it erupts, it deposits ash and other greenhouse gases that release into the atmosphere. Garbage is a very important one. What happens is they'll take the garbage and they'll put it through dump sites or landfills. As it decomposes, it produces carbon and methane gas, which are greenhouse gases. Next, you've got oil drilling. Drilling for oil uses fossil fuels, which lead to greenhouse gases. It also causes acidification of the oceans. So similar to natural gas drilling, as you start to drill, you will produce a greenhouse gas. Same thing with oil drilling. Power plants, also seen earlier. as we begin to use power plants, we use them to use thermal energy, the byproduct is water vapor, which is deposited in the atmosphere, and that is a greenhouse gas. Next is farming. So farming is a really common one because we all depend on it and it's very popular. So with farming, what happens is that as they start to produce their crops and take care of their cattle and livestock, they will produce nitrous oxide throughout the process, things like methane as well. So animals will produce methane, and a lot of the fertilizers, a lot of the products they use will also deposit more greenhouse gases into the atmosphere. And fertilizers again, but this is the actual fertilizer when used. So this links with farming as well. Typically what will happen is they'll use a synthetic fertilizer. Now this synthetic fertilizer has a chemical reaction which releases nitrous oxide, a greenhouse gas, into the atmosphere. But wait a minute. What is the Milankovitch cycles? Milankovitch cycles is a very interesting natural cause of climate change. We're going to see them right now. The term Milankovitch cycle refers to a cyclical movement related to the Earth's orbit around the Sun. Cyclical meaning it happens in cycles. So let's take an investigation into what these cycles are. What are these movements and patterns that the Milankovitch cycle is causing? Now there are three Milankovitch cycles. The first one is eccentricity. That's the path of the orbit. The next is axial tilt, essentially the angle of the Earth. And the third one is precession, or the wobble of axis. Together, they influence the amount of solar energy on the Earth's surface and impact the Earth's climate. Eccentricity refers to the path of the Earth's orbit around the Sun. This is elliptical in shape from less elliptical, so a perfect circle, to more elliptical and back, and is due to the gravitational fields of neighboring planets, particularly the large ones like Jupiter and Saturn. The measure of a shape's deviation from being a circle is called eccentricity. That is, the larger the eccentricity, the greater its deviation from a circle. So what does that look like? Essentially what will happen is, if the Sun is in the center, the Earth's path can start off as a perfect circle, so this would not be elliptical at all. But neighboring planets, for instance Jupiter, they will influence that path and cause it to be more elliptical, more oval shaped. Eccentricity comes along when this deviates. So as Jupiter becomes further or closer away, it will cause that to deviate as well. Now when we say eccentricity, what we're referring to is that different variation, that we can either go from elliptical to not elliptical at all, from oval to perfect circle. The impact is the closer you are to the Sun, the more heat, the further away, the colder it'll be. So one cause can be eccentricity. Of the orbit. The next one is axial tilt, the angle of the Earth. The Earth's tilt shifts between 22.1 degrees and 24.5 degrees and back. Greater tilts mean that the hemisphere closer to the Sun, so for instance during the summer months, they'll experience larger amounts of heat than when the tilt is less. So if you are in, for instance, we'll say North Africa, when you revolve and you face the Sun, if you are tilted towards it, you'll be more exposed to that heat and you'll have a hotter climate. If you happen to be tilted further away, you'll have a less aggressive climate. So in other words, regions in extreme upper and lower hemispheres will experience the hottest summers and the coldest winters during a maximum tilt. So think about if you're ever at a barbecue and you lean forward into the flames. You can feel that heat as you lean forward and then it dissipates quite quickly as you lean back. Strange example, but that's similarly what's happening here. As you lean forward towards the Sun, you have a different effect as opposed to leaning further away. And that is the second factor, the axial tilt, the angle of the Earth. You angle towards, you'll get more. You angle away, you'll get less. The next one, and the last one, is precession, the wobble of the axis. Precession as well as tilting are the reasons why regions near and at the poles experience very long nights and very long days at certain times of the year. For example, in Norway, which is very far north, the sun never completely descends beneath the horizon between late May to late July. So we said that if you lean forward, you get more. If you lean further away, you get less. That is the axial tilt. The fact that you wobble from forward and back is precession. Areas in the north, they will begin to wobble and they'll sort of stay in the blind spot where they will not really have certain things. For instance, they'll never really have a sunset in Norway because it keeps wobbling in that sense. And collectively, this is the Milankovitch cycles. Eccentricity relating to, looking at the left, eccentricity is relating to how the path of orbit brings you closer or further away from the sun. Obviously, the closer, the warmer, the further away, the colder. Tilt is the angle that you're leaning forward into or further away from the sun. And precession is leaning further away and from the sun. So that variation is precession. And those are the Milankovitch cycles, which can be seen as a natural cause of climate change. So between human and natural causes, take the Milankovitch cycles and put it in the natural causes. Now let's look at the impacts of climate change. Alright, so the temperature's gone up, there's a lot of greenhouse gases, so what? What's the impact? Well, considering that most people live along the coast, it actually is quite significant. Here we can see an iceberg on the left and a small settlement on the right. As the temperature begins to increase, that iceberg will begin to lose mass. That mass, becoming water now, will cause the sea levels to rise. As the sea levels rise, they will flood coastal areas. So one way it can impact is it can impact coastal areas. That's quite a big one. In the next one, we'll see how we can see these greenhouse gases lingering away in the atmosphere. As the sun gives us energy in the form of short wave, that long wave is prevented from re-radiating out back and it stays inside, keeping us warm. We've covered this a bit earlier. The problem is that as that sunlight starts to hit the earth, it warms up areas that it hits, and that causes a lot of different impacts. For example, if it warms down an area of land or the ocean, that will cause the air to become warm. And we know that warm things rise, so as it gets higher and higher, it condensates and forms clouds. Those clouds rain, so it could increase rain. So you might have extra flooding in that sense. As it heats up and goes up and up and up and like becomes a cloud and starts to rain, eventually it's going to sink. It's going to cool down and sink again. That sinking will prevent rain. So we can see the grey arrow is showing how it will prevent rain. Now, if you live in that area, imagine how hard it's going to be for you to form clouds. Pretty difficult. The next one, which is the slice there, suppose it's a colder month. If the air has no opportunities to warm up and it's always cold, that's how we get snow. If those conditions increase, we'll be getting more and more and more snow. It will begin to pile on thicker and heavier. So it actually can cause less snow and more snow. So it's quite a complex concept. So climate change can make weather more extreme, leading to more storms, floods, snowfall, and droughts. So it's quite significant and has a major impact in that sense. Another way is that growing foods can become more difficult as ecosystems suitable for crops become more difficult to sustain and animal habitats shift to new climates. If you have a certain specific condition you need to harvest pigs or grow grapes, and climate changes, that puts a real hindrance on your ability to grow food. So it can really affect the way that we eat, our health, our nutrition. So it's important in that sense. Finally, one other example is pollution. Increased temperatures increases the ozone particles in smog. So smog is a horrible thing. It causes things like asthma, heart disease, and lung cancer. Increased temperature, increased ozone particles, more air pollution, more sickness. So it can affect your health. And that is climate change. We have seen the natural and human causes, the impacts on people and the environment, and greenhouse gases. Next, let's look at atmospheric circulation cells. Atmospheric circulation cells refer to the 6 wind belts on the planet. Here we can see them divided in slices. What we want to focus on is how these slices are divided. They each have a name depending on which section is referred to. At the very top at the poles is the polar. These are the polar cells. It's typically sinking air, it's quite cold. Then you've got feral cells, which are found between 30 degrees and 60 degrees north-south. Finally, from the equator to 30 degrees north or 30 degrees south, you have the Hadley cells. Now, I would recommend you coming up with some kind of mnemonic to remember these. So something like pole fell hard, hard fell pole. So you know that if you're starting from the top, falling down, and then play it reverse, it will tell you which one it is. So these are essentially the atmospheric circulation cells, and they each play a very important role in moving warm and cold air masses around. You'll notice along the equator, for example, the Hadley cells, they begin to push air up at the equator. That causes air to rise. As it rises, it condenses, and you've got a lot of clouds there. Between the feral and Hadley cells, it's a sinking. So that would mean that all the air in that area is being pushed down. It's a very high pressure system. It means it's under an immense pressure from the equator. And what that does is it means it's harder to grow rain, and most of the deserts are around 30 degrees north and 30 degrees south. So I would like you to think, what are the atmospheric cells, and put them in concept of polar at the top, then feral, then Hadley again, then feral, then polar. Here we can see the purposes of each of them quite clearly. When you get direct solar energy at the equator, that causes the air to rise, so you've got a lot of clouds and it rains a lot, so that's low pressure. As the Hadley cells begin to combine with the feral cells, it will cause a sinking, so now we have high pressure. Once the feral cells and the polar cells max, you've got low pressure, and then the polar cells then create high pressure at the poles. So each of these can either cause lots of rain, or little rain, heat, or cold. So they all have their very unique and very useful purposes. And that is the atmospheric circulation cells. Now let's have a look at cyclones. Also known as hurricanes, depending on where they form. Now, for the sake of shorthand, I'm going to be using the term hurricane. So essentially, a hurricane is a large-scale air mass that rotates around a strong center of low atmospheric pressure. It goes counterclockwise in the northern hemisphere and clockwise in the southern hemisphere as viewed from above. So we can see that it's a simple demonstration in the bottom. Northern hemisphere will go counterclockwise, southern hemisphere will go clockwise. Now, there are certain conditions that you need for a hurricane. At first, you need it to be at least 27 degrees Celsius. So if you need it to be quite warm, what does that suggest? Well, it does kind of suggest that most should occur around the equator, where it's the warmest. And that is actually what we find. We'll find that most hurricanes form along the equator within the tropics. So the tropics is between the Tropic of Cancer and the Tropic of Capricorn. Now, the way that hurricanes form is actually quite interesting. What will occur is that warm waters will begin to evaporate. This creates warm, moist air, which acts as fuel for the storm. An additional component which is quite needed is wind. Wind adds to that evaporation because it moves the air around. So wind is also needed as it evaporates more warm water into the atmosphere. So if you think about warm waters just like lingering just on the surface of the water, you got a wind comes along and it sweeps it up and you get more of that moisture in the air. Most hurricanes that hit the USA are caused by winds across the Atlantic from North Africa. This is because if you think of where the equator line is, and the fact that the Earth is round and it spins, we can see that as the hurricane on the northern hemisphere begins to spin counterclockwise, it will have a trajectory from right to left, from east to west. And that is what we'll find. So essentially, the warm air rises into the atmosphere because heat rises. So it's being really, really warm and that heat is going up. What will happen is that it will eventually start to cool and form cumulus clouds. So the warm water is causing moisture. The air kicks that moisture up and up into the air. As it goes up and up and up, it will form clouds. From here, that continuing gust of wind will keep that moisture going up, so it will cause the warm air to continue to rise upwards and upwards. It also continues to blow and cause the wind to move in a circular pattern around its center. So the wind in this situation is doing two things: warm air making it rise, and causing that rising amount of air, turning into cumulus clouds, to begin to spin around itself. The spiraling winds begin to gather a cluster of thunderstorm clouds, fueled by warm, humid air. So as it begins to spin and spin and spin, it will start to attract more and more and more clouds until eventually they start to grow and they start to gain more momentum and more mass, until eventually you've got what we understand as a hurricane. Once the spinning winds reach 74 miles per hour, that's when we classify it as a hurricane. So it only becomes officially a hurricane at 74 miles per hour. Now, hurricanes can get very, very big. They can reach about 10 miles high and 1,000 miles across. That's the distance from Florida to New York. So it's quite a distance. Once a hurricane is formed, so it's reached 74 miles per hour, and it starts to approach land, as soon as it goes on top of land, it starts to weaken. That's because once a hurricane hits land, it begins to run out of that warm, moist air that is what fuels it. So as it goes over land, its winds begin to weaken. So as you can see from this GIF, we can see that the hurricane's strength is dramatically decreased the second it goes over land. And that's because it's losing that fuel which is keeping it going. This diagram shows the structure. It's almost like the hurricanes have a plumbing system. We can see that it's quite warm in the center. As it rises, it adds more and more clouds and it adds to that mass. But when it goes up, it eventually cools down and falls again, which then goes back into the cycle. So the cool air goes down, which just recycles, and now you've got warm air going up. In this one, we can see how the eye of the storm, having high pressure, so high pressure skies, it's impossible to have clouds in high pressure skies. So around the wall of the hurricane is very low pressure. So it's going up, it's really warm, so it's rising. As it rises, eventually it cools down and it sinks. As we can see on the edges, it begins to sink. That then has a nice little cycle where it goes up and down, and it keeps going these nice little gyres almost in the center. And that causes the hurricane to keep going, and it gets fueled by that warm, moist air. Now let's look at the Saffir-Simpson Hurricane Intensity Scale, which is how they characterize a lot of these hurricanes. According to this scale, they have 5 categories, depending on the wind speed attained. So a Category 1 would be something like 74 to 95 miles per hour. Category 2 would be 96 to 110 miles per hour. 3, 111 to 129 miles per hour. 4, 130 to 156 miles per hour, and finally number 5 is 157 and more miles per hour. So anything in excess of 157 miles per hour, you would be calling it a hurricane category 5. Now sometimes you come across a diagram like this which shows the intensity and pathway of tropical storms. This particular one is showing from 1950 to 2018. Now notice the distribution and density. We can notice the path. The equator is untouched, and there's not that much on land. It seems like the most you can get on land is a category 1 or maybe a bit of a category 2. It loses so much energy as soon as it goes over land because it's just constantly being fueled by that warm, moist air. I'm going to give you a second to admire this because I think it's quite cool. This is another interesting diagram. This one will show the areas in which tropical storms form and the path. Notice the path is always east to west, and they always revolve around the equator. So they always form around the equator. They need those tropics area. So it's essentially confined within the tropics. It needs those equator winds, high speeds, it needs warmth, and the area that gets the most warm on the Earth is within the tropic. So here's a nice illustration of just how it all works. You'll also keep note to earlier on when I said that the names change depending on where they are. Hurricanes, northern hemispheres near America, cyclones near Africa and Australia in the southern hemisphere, and typhoons near Asia. Same thing, it's just where they develop they get a different name. Here we see them side by side. On the picture on the left that tracks the intensity of all tropical storms, this is again from 1950 to 2018. TD is tropical depression, TS is tropical storm, and then you've got your hurricane category 1, 2, 3, 4, and 5. Now let's look at the impacts of hurricanes. Obvious one, hurricanes can destroy homes and businesses. They're strong enough to peel the roofs off of houses, to destroy entire cities, suburbs gone. They really destroy quite a lot and pretty efficiently as well. The winds are really, really high speed and they can cause a ton of damage to the point where you can destroy an entire house, just suck it up into nothing. Hurricanes can also destroy the sewage pipes and they spread diseases. If you have something which is far away and kept for the right reason away from the water supply, and a hurricane comes along and bursts a pipe and contaminates that water supply, that will spread diseases. So it can destroy people's health by spreading disease. Another one is that hurricanes can destroy ships. If they get too close to the dock where there are ships sailed, you'll find that they'll just get destroyed completely. Hurricanes also cost billions of dollars in damages. So it's a huge burden on the economy, it's on people's businesses, and it's quite a deterrent. If you would imagine you were in an area and you had a shop, and then that shop was completely destroyed every 5 years, would you stay? Would you start your business? It's a huge pressure and it's quite demoralizing to the people in the area. And it's very expensive as well. It can make a huge amount of damage and that costs billions of dollars. And that is cyclones. We looked at the social, economic and environmental impacts as well. So next thing is droughts. We'll be looking at the human and natural causes as well as the impacts on people and the environment. As with before, let's get some key definitions out of the way. Drought is a period of time when an area or region experiences below normal precipitation, so it doesn't rain as much as it normally does. The lack of adequate precipitation, either rain or snow, can cause reduced soil moisture or groundwater, diminishing stream flow, crop damage, and a general water shortage. So anytime the water shortage is being reduced to the point of it causing problems, we will call that drought. Three main types of drought. There's meteorological drought, which is when the amount of precipitation received in a specific area is less than average. So in any given year, if the rain levels are much lower than what we would expect, we would call that a meteorological drought. The second is a hydrological drought. This is when the reduced precipitation impacts on water supply. This is things like decreased stream flows, soil moisture, reservoir and lake levels, and groundwater. So when meteorological drought, the reduction in rainwater, and in rain in general, causes issues with the water supply, it becomes hydrological drought. The final type is agricultural drought. That's when the above two types of drought impact on agricultural activities. So things like reduced soil moisture or reservoir levels required for irrigation. So as soon as a meteorological drought, which is the reducing of rain, causes problems to the water supply, we've got hydrological. As soon as that impacts on agriculture, you've got agricultural drought. And those are the three main types of drought. Now there are many different causes for drought. We're going to be looking at the human activities that cause it first. Things like agriculture. Using large amounts of water to irrigate crops removes water from lakes, rivers and groundwater. Some crops require more water than others, for example, cotton. So farming practices can have a higher demand on water, and in the long term that can start to siphon a huge amount of that water supply to the point where it could cause hydrological drought. It could cause there to be much less water than is needed. Dam building is another one. Having large dams built across a river to produce electricity, so this is hydroelectric power, where they'll have those turbines we saw when we looked at energy. We'll just have them in the water, so as the water rushes through it, it causes it to spin, which moves an axle, and that moves the copper wire and magnets, and that produces power. So they use dams to produce that kind of power, but instead of steam, they'll use water. So large dams can be built across a river to produce electricity and store water in a reservoir. This can reduce river water flowing downstream and cause drought below the dam. So if you're collecting water in one area, you must have taken it from the areas more downstream, below the dam. So maybe building a dam, which might produce power and it might be good for one area, is causing drought in another area. Another example is deforestation. Removing trees can remove the amount of water stored in the soil, as rain tends to fall and wash off the land as surface runoff. This leaves the ground vulnerable to erosion and desertification, which can lead to drought. If you were to imagine laying on a beach, and there's a hot sun, and you have an umbrella, that umbrella is providing you with shade, and that keeps the moisture in your body relatively hydrated. If you were to take the umbrella away and you're exposed bare to the sun, it will start to cause you to be dehydrated, it will start to dry you out. Now trees do this. You have soil which has some moisture in it, and the sun will shoot at the soil, but it gets blocked by these trees, so the moisture remains in the soil. If we deforest and remove more and more trees, you've made that soil more vulnerable, and through making it more vulnerable, it's now more likely to dry and erode. So now you've got less moisture and it becomes a dry, drought-ridden former wetland, essentially. The result of this is erosion of the land and desertification, the growing of deserts. Finally, there is climate change. It's predicted that climate change will cause some spaces around the world to get hotter, which will increase evaporation, and some areas to receive less rainfall, both increasing the risk of drought. So if we can create more evaporation, that takes the water and brings it more into the atmosphere, and that also reduces rainfall. So it's a lose-lose situation. So these are just 4 examples of how human factors can contribute to drought. Now, what are the impacts of drought on people and the environment? Essentially, we can divide these into economic, social, and environmental impacts. For economic, farmers may lose money from destroyed crops. So if their business and their entire livelihood revolves around producing a certain amount of crops and providing that service, if a drought takes that away, that's a massive amount of economic loss. Ranchers can spend more money to feed and water animals. So there's not enough water, so now we have to make up the expenses, and that's going to cost a lot of money. A decrease in production could increase the price of goods. For example, if you were to manage to decrease the production of dairy, that will increase the price of cheese. Lastly, for economic, food supplies could shrink and habitats can wither. So the food supplies can become shorter, which would mean that this price would go up. And that is for economic. Going to social, we can see how all of the economic losses could cause depression and anxiety, could cause mental health risks. It could also cause physical health in the terms of heat stroke. If there's a higher temperature and there's not enough water, that could cause heat stroke. And there could even be conflicts over water. If you're in an area, a rural area, and you go through a drought, you might be able to be desperate enough to start going against your neighbor because he watered his fields too much and it's actually his fault, and you might end up having a conflict over that. Or there might be a certain reservoir and people might conflict, I need that reservoir more than you, give it to me. So there could be conflicts over water. Finally, for environmental, you could have things like trees drying, which would cause the risk of wildfires to increase quite substantially. And lastly, there is soil erosion. The soil could erode away, and that could cause a real harsh problem. So these are the impacts of drought, economically, socially, and environmentally. But now we're going to be looking at the physical causes of drought. We saw the human causes, but now let's look at the physical. Before we do that, let's look at the normal conditions. So, if this is the world, the main causes, the physical causes of drought are found in the Pacific Ocean. To assist us, first let's mark the equator line. So that is where the equator is. Now what we're going to cover is the normal conditions. So normally the trade winds will blow from east to west. These trade winds will push warm water nearer to the surface, as we can see here. All of that push is pushing the warm water closer towards New Zealand and Australia. As the warm water is pushed away from the coast, it's replaced by cold water pulled up from deeper down in the ocean. This process is known as upwelling. So the trade winds are going to push all the warm water to the west, towards Australia and New Zealand, and in its place, cold water from deep in the ocean is going to fill that void, a process known as upwelling. Now the result of this is that the warmer water concentrates in the west and the colder water concentrates in the east. As the warm air rises, and we're talking about the left pass towards the west, as that rises, it condenses and starts to rain. Eventually it sinks as it cools. So here we can see the trade winds pushing most of the warmth to the west. That warm air is going to rise. As it rises, it condenses. You've got yourself a lot of clouds on the west. But as that water, the warm air starts to cool down, it will sink and create two things. A low pressure system on the west and a high pressure system on the east. Low pressure systems covered in clouds, high pressure systems, clear blue skies, no clouds. So in this situation, very, very normal. That's what normally happens. El Niño is the exception. This is when the normal conditions deviate into the extreme and cause drought. El Niño means the boy, and it was named as such because it happened around every December. It's a reference to Jesus Christ. During an El Niño effect, what occurs is the trade winds, they begin to weaken. So they push less warm water to the western side, which causes less upwelling on the eastern side. And that causes a very unique phenomenon, as seen here. That shift in the trade winds going from pretty strong to quite weak, that makes massive changes. So this changes the rainfall and the wind patterns over the Pacific. The changes in wind is what impacts the temperature. Now, because the most brunt of that temperature is more around the center, as that warm water starts to heat up and then that causes the warm air to rise and start to condense and rain, it will sink, but now in both directions. So instead of one being rainy and the other one being dry, now they're both going to be dry. And this will impact the amount of rainfall you get because it's created two high pressure systems. What impact do you think this would have on Australasia and South America? Now we've seen that we had economic, social and environmental impacts. This would have a huge impact on the farmers, which would have impact on the sale of products, and could have impacts environmentally, causing certain fires, because now the trees are drier, so they're more easier to burn. So it has a lot of impacts on these areas. And that is the El Niño effect. Instead of the normal conditions that cause high pressure skies towards the east and low pressure skies towards the west, the El Niño causes high pressure skies on both the west and the east, limiting the rainfall. It also increases temperature. On the flip side, you have something called the La Niña effect, which means the girl. Now this does almost the opposite. This creates high pressure skies in around America and Mexico. Now with high pressure skies, that means less rainfall, and that could cause drought in the USA and Mexico. So the El Niño causes high pressure skies on the west and east. The La Niña can cause high pressure skies around the west, so around North America. Now this is a great diagram because it shows the difference between the El Niño and the La Niña effect really clearly. In the El Niño, the warmth is essentially concentrated in the center of the Pacific. It produces high pressure skies in both the west and the east. In the La Niña system, most of that warm cold current is being pushed towards the west. The concentration of warm moist air and warm water is towards the west. This produces a low pressure system towards the west and a high pressure system towards the east, or in this case would be America. So America would then suffer quite some drought. In the El Niño, both Australia and New Zealand and in Asia, they would experience drought, as well as Central America and South America. And that is droughts. We've looked at the human and natural causes as well as the impacts on people and the environment. Thank you for watching this YouTube channel. Everything you've seen on this lesson has been done exclusively in PowerPoint. So if you're a teacher and you would like to purchase these, please visit my test store. If you'd like to support the channel, please click subscribe.